So in the second part of this lesson, I'm going to talk more about the Java ReentrantLock as an illustration of how you can provide mutual exclusion to concurrent programs in Java. This is not the only way to provide mutual exclusion. You can also use things like synchronized blocks or synchronized statements or synchronized methods, which we'll talk about later in the course. So the ReentrantLock is a class that is used to provide mutual exclusion to Java concurrent programs within a process. It implements an interface called the lock interface, which you can read about here. And there's a bunch of other things that implement lock. So ReentrantLock does, Reentrant ReadWriteLock does, or Reentrant ReadWriteLock readlock, and Reentrant ReadWriteLock writeLock. Those are all things that implement this interface. Under the hood, much like the semaphore class we talked about a couple weeks ago, ReentrantLock applies the bridge pattern. So remember, the bridge pattern decouples the abstraction or the interface from the implementation, so the two can vary independently. In this particular case, the ReentrantLock is the, you can actually do this a couple different ways, but ReentrantLock is the abstraction. We don't really have a refined abstraction here, but we have ReentrantLock, and you can have this sync hierarchy, and as we'll see, we have fair sync and non-fair sync. So this really maps almost identically onto the bridge pattern, which is pretty cool. Here's what it looks like under the hood. There's a field in ReentrantLock called sync of type sync with a capital S. And sync with a capital S is a class that's an abstract class that extends something called abstract queued synchronizer, or AQS. Abstract queued synchronizer is a really cool framework that allows for FIFO wait queues. So if you want to read more about abstract queued synchronizer, take a look at this paper from my buddy Doug Lee, who wrote abstract queued synchronizer, and it talks about how they use that. Semaphore and ReentrantLock and Reentrant ReadWriteLock all use the abstract queued synchronizer framework. The cool part here is that you can have fair or non-fair semaphores. And that's basically done simply by having different subclasses of sync. As you saw over here, we can have fair sync or non-fair sync. So in the constructor for ReentrantLock, you can see that one of the constructors, there's a couple of constructors. This one takes a Boolean that says fair, and as its name implies, as the parameter name implies, if fair is true, what it'll do is it'll go ahead and select the fair sync implementation, in which case we'll have strict first in, first out fairness, right? So the order in which the threads get access to the lock is the order in which they show up. So we have fair synchronization. So that makes it fair, but there is some penalty for that because implementing fairness doesn't come for free. And if you have fair set to false, then it will be non-fair. So that makes it more efficient because the implementation can just pick whichever one happens to be the fastest to let go next, but it's not fair. So this approach, the non-fair one, supports barging, where you can barge in line. The default, if you don't specify one way or the other, is to be non-fair. So the default behavior of ReentrantLock is to favor performance or efficiency over fairness, which is usually the right thing to do. If you care about fairness, then you can get it, but it's not the default. Fair sync, as we will learn later, is a lot more complicated to implement. And the reason you will learn this later is you'll get a chance to implement a fair semaphore later. And that turns out to be substantially harder to implement than a non-fair semaphore. Non-fair semaphore, non-fair mutex, easy to implement. Fair, way harder, as you'll learn. So it's a lot slower because it's more complicated. There's a lot more stuff going on. So use it sparingly, or use it only when you need to. So as I mentioned before, there's this concept of a MonitorLock, which is used by synchronized statements or synchronized methods in Java for the built-in features of synchronization, the built-in monitor object features, which we'll cover in a week or so. And the core methods of ReentrantLock are almost identical to the semantics of the built-in MonitorLock, the thing that's using the so-called the intrinsic lock. And we'll talk more about that. So lock gets the lock, unlock, releases the lock if it's held. There's also a bunch more things that are provided beyond lock and unlock. And these are all things that you don't get by using the built-in Java synchronized statement, synchronized method. Those things are not provided with that. So for example, you can acquire the lock interruptibly, which means if someone interrupts you, you'll return, whereas that's not the way it works with the locks in Java synchronized methods and statements. There's also ways to try to conditionally acquire the lock, either check to see if it's locked and only lock it if it's available, or wait up to a certain amount of time. So you can't interrupt Java's synchronized methods and statements. So these are more flexible. And likewise, you can't do non-blocking operations on Java's synchronized methods and statements. Another thing that is interesting about ReentrantLock is it supports so-called recursive mutex semantics, or Reentrant Mutex semantics. You can read about that here. And I'll show you essentially how this works. So the way this works is, as you'll see when you start out, if you start out with the lock unlocked, and when someone locks the lock, the current thread that locked the lock will own the lock, and the count goes to 1. And this allows the thread to come along and lock again on the lock. The same thread that owns the lock can relock it without incurring self-deadlock. You don't have to worry about deadlocking. It just increments the count by 1 atomically. So this is a convenient type of thing, and we'll see some examples of why. Now, there's pros and cons with this approach. The good part about ReentrantLock is it is very useful in programs that need to recursively do work that reacquires the lock. So it makes certain kinds of programs a lot easier to program. The downside is it's slower to have a reentrant lock than a non-reentrant lock. And if you take a look, here's actually some of the code. This is the code from ReentrantLock. This is actually a snippet of the Java code for ReentrantLock. And you can see here what it does. If you try to acquire a lock in a NonFair model, NonFair try acquire, it figures out the current thread, figures out the current state of the lock. It goes ahead and says, if this is available, then let's go ahead and try to acquire it. If we do, we're done. Otherwise, we're going to go ahead and check to see if we own the lock. And if we do, then we go ahead and increment the count and set this state atomically. So there's additional stuff going on here. Whereas if we didn't have to do reentrancy, we just have to do this atomic compare and set. So that would be a more efficient way of doing things. So why on earth would you ever need to have reentrant locks? What's the benefit of recursive mutex semantic? And here's a good example. This is actually straight out of Android. And the example here is if you have a framework that needs to hold a lock during callbacks to user-defined code where the framework doesn't know if the user will want to reacquire the lock or not. And so recursive locks are very important here. So let's take a look at a simple example. This example comes from my ex24 folder at my GitHub account. And it uses something in Android called a countdown timer. And a countdown timer is a kind of a cool Androidism where you make this object, you make an instance of a countdown timer, and you give it the initial tick count. Like you say, I want this thing to run for 30 milliseconds. And once every millisecond, I want it to call me back. So you could imagine like a countdown, like you're going to launch a rocket or something like that, 10, 9, 8, 7. And every time a millisecond elapses, this thing will call back to user-defined code, which can do stuff. And sometimes the user-defined code might update a GUI, but sometimes the user-defined code might want to decide to prematurely cancel the timer. And so let's take a look and see how this would all work. So we'll take a look at a couple things. Here is, this is the code for cancel. Here's the code for onTick. This is a hook method that gets called back that you can override. Here's the run method that we're going to have on our timer handler. This is just implementation stuff. This is what's actually running in the background doing this countdown lock. And the way this works is that when the run timer in the background thread runs, it goes ahead and acquires the lock, because there's some internal state for managing the countdown timer. And with the lock held, it calls the onTick hook method. So it calls the onTick hook method, which is this thing, with the lock held. And that's because it needs to hold the lock while it's doing this stuff, because someone could come along and do other things in other threads to access the state of the countdown timer. And let's say, for sake of argument, that the onTick hook method, which is what the user defines, right? This is framework code. This is user-defined code. The user-defined onTick hook method might decide to call cancel. It might say, I'm done with my processing. I want to prematurely exit this countdown timer. I'm out of here, or I want to be out of here. And as you can see, what cancel does is cancel reacquires the lock, because it's going to change the state. It's going to change the state m canceled to true. And it doesn't want to do this without holding the lock. But note that that lock has already been held in this guy, who is the one that called onTick, who's the one that called cancel, who's the one that reacquires the lock. So this is a recursive lock. And if we don't have recursive lock semantics, then when we call lock, the second time in, it'll end up deadlocking on itself, which would, of course, be a real pain in the butt, right? Okay, so that's basically the overview, or that's an overview of ReentrantLock, kind of motivating why it's reentrant, and a little bit of how it's reentrant as well.